Okay, this is the part 2 of thermodynamics in chapter 5 of the Burdge book. So we'll pick up here and we'll see how far we get. So the last thing we talked about in part 1 was the types of systems. It's important that you define the system, and the system is what you're interested in studying. And the three types of systems that you'll come across are an open system, which allows both heat and matter, or if you want to say energy and matter, to be exchanged. And that is what is under A here. And under B is a closed system. And a closed system does not allow matter transfers, but it does allow energy transfers or heat transfers. And then the most rare of the systems for us would be the isolated system. And an isolated system does not allow energy or matter transfers. All right. So make sure you define the system carefully. There's going to be a system. Generally, there's a boundary to that system, and then you have the surroundings. And when you add the system plus the surroundings together, you have the universe. All right, first law of thermodynamics. We've actually already seen this, but let's refresh our memories what we have here. Instead of saying U for internal energy, I use the delta E of the system plus the delta E of the surroundings. When we add those two energies together, it must equal 0. A more compact way to write that is delta E of the universe is equal to 0. The change in energy of the universe equals 0. And the way we get about that is whatever is lost by the system must be gained by the surroundings, or vice versa. So this is the first law of thermodynamics, the conservation of energy. All the energy in the universe is here. And then all we can do is convert energy from one form to another. So delta, remember what it means. Delta means change. And the change is always final minus initial. So just keep that in mind. And again, this book uses delta U, which is more practical in physics, so I don't have any problem with using delta U. It usually means internal energy. It could also be written again, delta E equals the E final minus E initial. So it could be that as well. And we're focused only on the system. We're focusing only on the system here. All right, so energy is the ability to do work, and the types of energy that we're going to focus on are heat and work, and the type of work we're going to look at as far as chemistry goes is pressure volume work. So this equation shows the change in energy, the internal energy of the system, and the change of the, again, system's internal energy is given by heat plus W, which is work. So work is has a very specific definition for chemists here. We're going to say that work is equal to negative the pressure times the change in volume. So let's talk about this. Let's look at a system. So here's my system. Here is a piston which represents the pressure on the system. All right, so there's my piston here. Okay, so if this is my system and I want the system to do work on the surroundings, then what has to happen is the piston has to move upward. All right, so let's say the piston moves up to here. I'm having some problems here. All right. Oh, I know what it is. Okay. So here's where we started. here's where we end. That's the change in volume. All right, that's the change in volume from here initially to here finally. So if I take, remember change is final minus initial. If I take the final here minus the initial here, I will get a positive value for the volume change. It'll be a positive value. So like if this is 4 and this is 3, 4 minus 3 equals 1. So we get a 1 here. A positive 1, okay? So if this is positive, and pressure is always positive, you can only have 0 pressure or some positive value. So this value is positive and this value is positive. The reason why we have the correction factor of a negative sign here, which is really important, is remember that if the system does work or releases heat to the surroundings, we give it a negative value. And that's by convention, all right? So when work is done by the system on the surroundings, and the heat released here is exothermic, that means it gives off heat to the surroundings, both of these terms will be negative. All right? And so the more negative the term, the more energy that's released by the system, and the system is in a lower energy form. So think about the ball rolling down the hill. It had more energy up here. It ends here. And so when it goes from here to here, this is the final. This is the initial. If the final is, let's say, 1, and the initial was 6, we would have 1 minus 6 equals negative 5. So that negative there tells us that we are dealing with something that's releasing energy from the system to the surroundings. So that's why this negative convention is really important. And you know that this is at a lower energy than this is. And you can tell that by just the placement, or if I drew a y-axis and then reaction progress, or whatever you want to say, process on this side, you can see the final is at a lower energy than the initial. So neither heat nor work is a state function. They depend upon the path, which makes sense because let's look at work again. Work is equal to, in the simplest form, force times distance. And heat is the temperature change, and we get a flow of heat, but again, there's a path there. How far does the heat have to travel until it reaches the part where it starts to lower or raise the temperature, actually raise the temperature, right? So neither heat nor work are state functions. They are pathway dependent. All right, so the sum of heat and work, delta U, does not depend on the path between the initial and final states. So U, the internal energy or energy, is a state function. So keep this in mind that U, also written as E, energy, is a state function. Because what we're doing here is I ask you how much energy we have here, how much energy we have here. It doesn't matter whether it happens, it goes up and down and eventually ends here anyways. So it's pathway independent to get from here to the resting point to where we were at the beginning. So energy is pathway independent, but heat and work are not. So keep that in mind. All right, so let's look at a problem to show you how this all works. So calculate the overall change in internal energy, delta U, in joules for a system that absorbs 188 joules of heat and does 141 joules of work on the surroundings. Now, what I think is important here, if you can draw a picture of what's going on here. So what's going on is initially you have a system. We're going to write it as this boundary here. And initially we're going to say there's this much pressure on this system, which we symbolize as a piston. All right? So there's my pressure on the system, and inside here is my system. So what's going to happen is it says 188 joules of heat is absorbed by the system. All right? So that means heat's going into the system. That means that due to heat, which we'll just call H at this point, or if you want to say Q, let's do Q. All right, Q at this point, the heat's going into the system. That makes the internal energy of the system increase. But then it also says that the system does work on the surroundings. So that means that the piston has moved upward. Again, it means it's forced, the volume has changed. It has applied a force to what the piston represents, which is the atmospheric pressure. So we started here initially, and then it's moved up to here. There's a change in volume here. And it is going to, and the amount of work done, which would be, again, work equals negative P delta V, is equal to 141 joules. And that's what it says here, 141 joules of work on its surroundings. So here's where the sign convention becomes really important. So because the heat went into the system, it's a positive 188 joules. So positive indicates endo process. That means endothermic because we're talking about heat. So the heat is going into the system. And the work done, it is a positive value up here, but then you got to read the context, which says that work was done on the surroundings. So that makes it a negative 141 joules. And so that's why we see the negative sign here. The system is doing work on the surroundings. And when the system does work on the surroundings, or when the system releases heat to the surroundings, the convention is it should be negative. Here, the system absorbed this heat, so that's why it's a positive value. But here, the system did work on the surroundings, and that's why it's a negative value here. So when we add these two together, the change in energy is 47 joules. Now what that means is that after we've added heat to the system, and the system expanded against the surroundings, did work on the surroundings, we still netted 47 joules of energy for the system. So in the end, the system does have 47 more joules of energy inside the system than what we started with. All right? So that's a good problem. Make sure you know this equation. This is one that you need to memorize, that the change in energy of the system, that's what delta U stands for, change in energy of the system is equal to the heat plus the work. All right, so here is what we were talking about in the last slide, and they've got a table of this. It's so important. They've got a table, and then they've got diagrams or illustrations of it as well. So here's what you need to remember. The positive and negative does really mean something. So when Q is positive, that means heat is absorbed by the system. That means the heat is going into the system. It's an endothermic process. If heat is released by the system, it's an exothermic process. So the system is releasing heat to the surroundings. And Q would be negative. Negative means going out to the surroundings. Positive means going into the system. Work done on the system by the surroundings. That means we're decreasing the volume. If that's the case, W is positive because work is going into the system by reducing the volume of the system. Again, keep in mind, always keep in the back of your mind that work is equal to negative P delta V. So here the volume's decreasing. That gives us a negative value here. Pressure is always positive, and then when you multiply it by this negative here, you're going to get a positive value for work. And if it's a positive value for work, that tells you that the surroundings are doing work on the system. All right? Work done on the system by the surroundings, there's a typo here. This should be work done on the surroundings. This should be surroundings here by the system. All right, so that means the volume's increased. That means that you started again with the piston here, you ended up with the piston up here, so the volume increased from here to here, and therefore the system did work on the surroundings, and it should be negative. Again, what happens is volume change is positive, pressure is always positive, we multiply by the negative correction factor there, we get a negative value for work, which means the system did work on the surroundings. So there is a typo on this one, just be careful about it. And I think it's okay in the book, but just check to make sure. Really important table. I mean, this all really comes down to, why do you need to know this? Because the equation we're working with here is the internal energy of the system is equal to the heat and the work done by the system or on the system. So again, let's look at it graphically. So again, if you see heat leaving the system, Q is a negative value. Q is less than 0. If you see that the volume is expanding, and we know that work is equal to negative P delta V, again, delta V is positive, pressure is always positive, we get a value for work that is less than 0, then the system is doing work on the surroundings. But if the heat goes into the system, that's an endothermic process. Notice Q is greater than 0. And then as the pressure or the volume decreases inside of the system, then again, work equals negative P delta V. Volume has changed negatively. Pressure is positive. And then we have a negative here, the correction factor. And work actually comes out to be greater than 0. Work is positive. So you can tell that's important. We've spent like 3 or 4 slides on that and talking about it since the beginning of this chapter. It's important that you understand heat and work and how they apply to a system and whether that system's open, closed, or isolated. All right, so why do I need to know this stuff? Well, before we get into determining how many calories is in peanut butter, you have to know some stoichiometry again. So again, stoichiometry. If you've not gotten stoichiometry down from chapter 3, you've been dinged in chapter 3, you've been dinged in chapter 4, you've been dinged in chapter 10, now you're going to be dinged in chapter 5. So what reactions carried out at constant volume or constant pressure, enthalpy and enthalpy changes. And if you don't like the word enthalpy, just substitute heat. Heat and heat changes, if you want to think of it that way. And then thermochemical equations. All right, so we actually have done this, we kind of talked about this in chapter 10. So here's our airbag equation again. So inside your airbag is this sodium azide. And when and it's a solid, and when it ignites, it converts to sodium, solid, and nitrogen gas given off. And it's this nitrogen gas that blows up your airbag. And we actually did some calculations with this back in chapter 10. The equation's balanced. The phases are shown correctly. And so, again, what you start off with was this small volume of solid here. And then there's a flash. And then the increased pressure causes an increase in that increase in pressure, or the increase in gases here, inflates the airbag. So let's look at what happens. Is that here's a great way of showing it. So again, what does the piston always? It represents pressure. It represents pressure on the system. Generally, we think of it as atmospheric pressure. And so, again, here's our sodium azide. We add a spark, we get a reaction. And the piston, to keep the pressure inside and outside the system equal, all right, these two pressures, pressure of the system and pressure of the surroundings is equal. That means the volume has to change. So the volume goes from where the piston was, right here, where the piston was, to here. So this is the volume change. it's a positive value. Again, we plug that into this equation. The pressure is always a positive value. And then we multiply it by the negative correction factor there, and we get work equals negative. So in this case, the system has done work on the surroundings. Why? Because work has come out to be a negative value. We can see it here. We went from here to here. We can see that the pressure has been pushed. The volume has increased, pushing against the pressure of the surroundings, and the system's done work on the surroundings. And why does that happen? Because we went from a solid to 3 moles of gas here. So look at this carefully, think about it. Know that when you have positive volume changes against a pressure, against a force, then you're going to have done work. So here's what it really comes back to. Work is equal to force times distance. And we know that pressure is equal to a force per area. So all we're doing here is we're plugging in here for force, pressure over area. So you got the area of the piston, whatever the surface area of that piston is. And then you have so pressure times the area gives me the force. So there's my force vector. So we can solve for that. Let's just do that. Force equals P times A, right? So now you got the force, and you've moved it this distance here, all right? And so you know the distance. So there's a relationship between pressure, volume, work, and just work in general. All right, so reactions are carried out either at constant volume or at constant pressure. Okay? So what we've done here is we've taken the equation you're asked to memorize, delta U equals heat plus W, and we substituted in for W. W equals negative P delta V, the pressure times the change in volume. So we took this and plugged it in for the work part right there. All right? So if the volume cannot change, we put the reaction in a container that the container's volume is fixed and it cannot change. This becomes a constant. All right? That becomes a constant. And so then what we have is Q at constant. So if that's the case, then if this doesn't change, what's the value of delta V? If the volume does not change, V final minus V initial would equal what? If the volume does not change. 4 minus 4, 1 minus 1, whatever. The volume is 0. So this term becomes 0. This term becomes 0. And what we have here, there's a typo here. This is at Q at subscript V, not same as V. So this is a subscript. Q at constant volume is equal to the internal energy of the system. All right, so there's a typo here. This should have been subscripted. They didn't. And again, you can see here the P is subscripted. They made a typo there. So Q at constant volume is equal to the internal energy of the system. You go, why do I need to know this? This is the equation we use to determine how many calories is in a serving of peanut butter or potato chips or anything that you're trying, or how many calories or joules are in a ton of coal. This is the equation that we use. So we have to use an apparatus that has a constant volume, and we'll talk about that. Now, that gets pretty restrictive. That means we have to have a certain specialized instrument that has a container that can handle any pressure without exploding or breaking apart or something like that. So this is pretty specialized. But what you do in the lab is this. You are doing an experiment in a beaker, and it's open to the atmosphere. And again, I'm going to symbolize the atmosphere by the piston. All right? And the piston can freely move up and down. So at constant pressure, we get Q at constant pressure is equal to delta U, there's a typo here, plus P delta V work. All right, so let's look and see what happens here. So we bring in a new term, and that is called enthalpy, and it's a capital H. And H is called, enthalpy is heat under constant pressure conditions. So heat is equal to the internal energy of the system plus the pressure volume on the system. Now, again, this can't be measured directly. We don't know how much energy is in let's say a crayon. Let's say you got a crayon or a crown, whatever you want to call it, or a pen. You don't know how much energy is in the pen until you burn it, till you destroy it, till you deconstruct it. So this statement here is theoretical. And H is a state function, enthalpy. So all we can do is we got to measure changes in enthalpy. Changes in enthalpy. So changes in enthalpy is all we can truly measure. That is equal to the change in the internal energy and the change in the pressure volume of that system. Okay? Well, the pressure remains constant, right? We assume that when we do a chemical reaction, when we go from start to finish, we assume the atmospheric pressure is not changing through the course of the reaction. So that's why the P comes out here. So delta H, the change in enthalpy, is equal to the change in the internal energy, which we could find by doing heat at constant volume. So we can find this out by using a calorimetry experiment. And then we got to add in the pressure volume work done, this part. This is what's new. And the reason why that's so important, again, is because if this represents the atmospheric pressure, and then all of a sudden the atmospheric pressure takes over and causes the volume to get less in the container, then we know there's been some pressure volume work done by the surroundings on the system. So that's what this is so important. So if something contracts, you added two liquids in here and it actually contracted like this in the beaker, then you would know that the surroundings did work on the system. Now, most of the time it's just the opposite, right? You have a container, here's the piston, and then what happens is there's a gas generated, like it fizzes or something like that, and those bubbles of gas push against the atmosphere, and we actually have a change in volume that is positive because we started here, we end up here. That's a positive volume change. So chemists like enthalpy the best, and the reason why is if you think about all the experiments you did in lab this semester, you probably did them in open containers under atmospheric conditions. You didn't use a closed container or a fixed container that was not exposed to the atmosphere. So enthalpy is the main heat or energy that we look for in chemistry. All right, so here we have the change in enthalpy is equal to the change in the internal energy of the system plus the pressure volume work. So this change in internal energy is equal to, well, what is enthalpy again? The definition of enthalpy is heat at constant pressure. So what they did here is they solved for this. So they have heat and constant pressure equals delta U, and then we've moved this over here, so that's why it's plus P delta V. So see if you can manipulate that. Can you sit there and go, oh yeah, this is just delta U plus heat at constant pressure minus P delta V. And so delta U plus P delta V equals heat at constant pressure. And then we just flipped it to solve for that, all right? Now, if we substitute in for delta U this equation, All right. What we notice is this negative P delta V cancels out with this positive P delta V. And we get Q at constant pressure is equal to enthalpy. So you need to know that. I'm not asking you to derive it. It's important that you can follow the logic here. But again, what is the difference between Q at constant P and Q at constant V? This is equal to the internal energy of the system. This is equal to the heat under constant pressure. And again, the reason why we like this is because generally we're working with open beakers and we're open to the atmosphere, and we assume the atmosphere is not changing through the course of the reaction. So we have constant pressure conditions. We generally don't work with constant volume because it can be dangerous. If you've got a fixed container and you heat this up, eventually it's going to rupture the boundary. It's going to rupture the container and you have an explosion. So we'll talk about this in another slide here. So take the time, if you really want to understand this. I remember when I was in school and you're looking at this and the professor's talking about it and you're just saying, get me to the final equation so I can solve the problems in the back of the book. Well, in order to understand what's going on, you have to come back to this definition of what enthalpy is. All right? Make sure you understand that. And then that tied with what we already know is that delta U equals Q plus W, or delta U equals Q minus P delta V. This is what's helping you to get from here, what we see here, actually here's better, to what we get on the next slide. So follow the logic. If you can't follow the logic, I'm going to tell you to read that chapter, that section in the book a couple of times, because it's that important. It's that important for the understanding, not the mechanics of solving a problem, but for the understanding. All right, so enthalpy changes. We can't measure, again, I can't tell you how much energy is in anything until I destroy it and then see how much energy is either given off or how much energy is absorbed. So same thing with enthalpy. I can't tell you how much enthalpy is in a substance until it undergoes a change. So changes in enthalpy is the enthalpy of the products minus the enthalpy of the reactants. All right. So products, again, think of it like this. It's H final minus H initial. And the initial is the reactants and the final is the products. All right, so here's where the stoichiometry comes into play as well. So we had thermochemical equations. And you say, what's the difference between a balanced chemical equation and a thermochemical equation? Well, in a thermochemical equation, we not only have a balanced chemical equation with the phases of matter. Actually, this should not be subscripted. It should be like this. And your reactants and your products. So there's just a typo here again. This should look just like this G here. So we have a balanced chemical equation, but now we have an extra kicker here. We know what the change in enthalpy of this reaction is. So when this reaction occurs, when 1 mole of methane reacts with 2 moles of oxygen to form 1 mole of carbon dioxide and 2 moles of water, this reaction releases 890.4 kilojoules per mole of energy. Now, why did I say releases? Because when I see a negative sign here, it tells me this reaction is exothermic and that the heat is moving from the system to the surroundings. So you guys know this. This is natural gas. This is the main component, natural gas. You burn it in pure oxygen, and it heats your home if you have gas heat. And these are your two products. And this is how much energy is released when a mole of methane and 2 moles of oxygen react to form 1 mole of carbon dioxide, 2 moles of water. So instead of mole to mole ratio, you get mole to energy ratio. Look at all four of these values here, these terms. So instead of doing for every 1 mole of methane, I need 2 moles of oxygen. For every 1 mole of methane that burns, I get this much energy released. So you're going to treat it like a mole to mole ratio, but here it's a mole to energy ratio. And you're going to be doing some calculations with this. So this gets to be, I've got 5 tons of coal, how much energy can I get out of it? Or I've got 5 tons of methane, how much energy can I get out of 5 tons of methane? Well, you're going to have to take those tons of methane, and you're going to have to probably convert that to pounds, and then you're going to have to convert that to grams. And then once you get this to grams of methane, you're going to have to convert that to moles of methane. And once you get to moles of methane, you can come to your balanced chemical equation and see for every 1 mole of methane you get this much energy. So you're going to use this conversion factor to convert that from moles of methane to kilojoules of energy. So, looks much like a stoichiometry problem, works much like a stoichiometry problem, but instead of mole to mole ratio, it's mole to energy ratio. So, what's important about a thermochemical equation? You must specify the states of all reactants and products, because there's a big difference between if H2O liquid is formed and H2O gas is formed. So gas has more internal energy, so not as much energy is going to be released to the system if H2O gas is formed as a product. Some of the energy required to go from a liquid to a gas has to be absorbed by the water to convert it from the lower energy phase to the higher energy phase. So it's super important that you list all physical states. Now the equation has to be balanced just like a chemical reaction, and if it's not balanced correctly, then you have no shot at getting the answer correct. So to drive this point home, we can look at well, let's look at another slide here of how this works. If this is my balanced process, this isn't a chemical equation, right? All we're doing is taking solid ice and converting it to liquid water, and that takes energy. Sure it does, because liquid water has more freedom of motion than a solid, so we've had to reduce the intermolecular forces so that the water molecules can slide around each other, and that requires energy to do that. So this is an endothermic process. How do you know for sure? Well, if you got a positive value, it's endothermic. Or if you see the energy on the reactant side of the balanced chemical equation, you know it's endothermic. So what this slide is saying is that if I want to multiply this entire equation by 2, I must also multiply the delta H by 2. So whatever multiplier I use here to hit this coefficient here, I must also multiply the energy by that 2. Makes sense. You burn 1 piece of wood, it gives off a certain amount of energy. You burn off 2 pieces of wood that are the same, you get twice as much energy off. So that's pretty easy to understand. All right, so this is showing that if we reverse the process, if this is the combustion of methane and we get carbon dioxide and water, then if we flip the reaction, carbon dioxide and water produces methane and oxygen, and that would be an endothermic process. So if it's exothermic in this direction, it's endothermic in if we do the opposite. If we do the opposite, which is this equation here. So so this is the way coal works, right? Or let's look at natural gas. So you had carbon dioxide came from plant materials and whatever, and that combined with water, and it gets pressurized and it underground and so forth, and it actually forms methane. So we inputted this much energy per mole to form methane and oxygen. So now if I take the methane out of the ground and I burn it in pure oxygen and I get carbon dioxide and water, that much energy has to be released. So it's just showing that the forward reaction, if it's negative 890, the reverse reaction has to be a positive 890. Again, why? Energy is not created or destroyed, right? And so if the forward reaction is exothermic, then the reverse reaction has to be endothermic. All right, so let's put this all together. Let's look at like the type of problems you could expect here. So we have water works with carbon dioxide or combines with carbon dioxide. That's my two reactants to form sugar and carbon dioxide. All right, this is important because, again, plants need sugar in order to grow, and they can be converted to starches and things like that to make plant cell walls. But here's the reaction, and it's an endothermic process, positive 2,803 kilojoules per mole. So what they want to know is how much solar energy is required to produce 75 grams of this sugar. 75 grams of sugar. So what you have to start with is 75 grams of sugar. And they want to know how much energy is required. Well, our balanced chemical equation, even though mass is the underlying thing, we have each substance has a different mass. We've got to find out what the molar mass. So it's just a stoichiometry problem, right? First thing we have to do is we have to convert the grams of sugar to moles of sugar. So we have to find out what the molar mass of this compound is. 6 times 12 is 72. And then we got 12 times 1, which is 12. And then 6 times 16 is 96. And if we add 32 and 72 and 12, that's 84. 84 and 96. Yeah, 96 looks terrible, right? 96 equals 180. So there it is. 180.2 grams per mole is the molar mass of this sugar. Okay, so we know how to do this. This is chapter 4 stuff, chapter 3 stuff, or actually part of chapter 1. So we use molar mass to convert mass of sugar that we have to moles of sugar. Now, why do we do that? So we can relate it to our balanced chemical equation. So from our balanced chemical equation, we see for every 1 mole of sugar formed, this is how much energy has to be released. So we're going to use that as a mole to mole ratio, or mole to energy ratio. All right, so we have 0.416. That's how many moles of sugar we have formed. All right, so that's why so let me tell you what they've done up here. They've taken the balanced chemical equation, and they're going to use this as a multiplier to make this 0.416 moles of sugar. All right, see how that works? So 0.416 times, it's a 1-to-1 ratio, right? So for every 1 mole of this form, this much energy is released. And so 0.416 divided by 2803 kilojoules per mole gives us this much energy. All right, let me just make sure that's correct. So on your calculator, take 0.416 and multiply that by 2803. And you get 1.17 times 10 to the third kilojoules. The moles cancel out here. All right, so that's how much energy is required in the form of sunlight which is consumed to form 75 grams of sugar here. All right. So again, I don't know why they show it quite like. Let's see. They're trying to say, I don't like the equal sign. I mean, what I would have said is they're taking this that we have, how much sugar we have in moles. We're doing our mole to mole ratio. For every 1 mole of sugar, I get 2,803. So This is like more like a continuation, like we're going from here to there. Not like a delta H and you're trying to solve for it by dividing both sides by 0.416. That's just bad notation there. Okay, that's where we'll stop here, and we'll pick up from here later on.